We want to look at this question related to an exponential random variable. So here we're told the time and hours required to repair a machine is an exponentially distributed random variable with parameter lambda. So let's first define a random variable. Let the random variable x denote the time in hours required to repair a machine. X is exponentially distributed with parameter lambda is 1 by 2. So it's the information given in the start of the question. Let's do part A. Part A says what is the probability the repair time exceeds 2 hours? Probability X is greater than 2. Now the two approaches, the first approach is we'll use the PDF and the second approach we'll use the CDF because we have a closed form expression of the CDF for an exponentially distributed random variable. We could use that as well. The first approach is use PDF. Why we're using the PDF? Because we know for any continuous random variable, the area under the PDF gives us probability. And we know we can find the area under the curve using integration. So if we integrate the PDF over a certain interval, it will give us the probability the continuous random variable lies in the interval. That's why you can use the PDF because area under the curve is going to give us probability and we can find the area under the curve using integration. Now in this case, the PDF for this exponential random variable is of the form. Let's write its PDF fx of x. So its PDF is, we know, lambda e minus lambda x, which in this case would be 1 by 2 e minus. This is true for x greater than equal to 0. And it's 0 otherwise. Right, so here one thing that we really do need to keep in mind is this, right? X, we know continuous random variable takes on those values where its PDF is non-zero. So X takes on all values greater than equal to 0, right? Where its PDF is non-zero. Any continuous random variable takes those values where its PDF is non-zero, where its PDF is non-zero. And we should always, right? Whether it's a discrete or a continuous random variable, we should always note what values does random variable take on. Does random variable take on? For continuous random variables, the values they take on, right, are where the PDF is non-zero, right? So you should always keep in mind that. So we want to find now probability x is greater than 2. We can find this by integrating the PDF over this interval. Now probability x is greater than 2 essentially means here we know the exponential random variable takes all values greater than equal to 0. So probability x is greater than 2 means the probability x is between 2 and infinity. Right, so this is essentially probability x is greater than 2 and less than infinity. Where does this infinity come from? It comes from because we know x takes all possible values greater than equal to 0. Right, so that's what's important to keep in mind the values and random variable takes because we can be more precise about what probability we're finding. So probability x is greater than 2 less than infinity. Then this becomes, we integrate it from 2 to infinity. So we're going to integrate the PDF over this interval and then we can solve it. So let's just clear this up and let's write it down over here again. So probability x is greater than 2. So because this means this is essentially the probability x is between 2 and infinity. So we're integrating this from 2 to infinity. Right, and let's just take the 1 by 2 out and the integral of e, we know, okay, the integral of eax is just eax by a. So this is like recall. This is like integration. Right, so this we can write minus 1 by 2x divided by minus 1 by 2 to infinity. Right, and then you just simplify this a bit, like this minus 1 by 2. We'll just simplify this with this 1 by 2 over here. And then this becomes e minus 1 by 2x, 2 to infinity. Now we'll just plug in the limits. When you plug in the limits, e power minus Infinity is essentially 0 minus e minus 1. So this is just after plugging in the limits, and we get e minus 1 as our answer. So now one approach was you could use the PDF. Now approach two is we can use this CDF. Let's see how would we use that, because we have a closed form expression of the CDF, so we can use that. So approach two here is use the CDF, because we have a closed form expression of that. We don't have to find it from the PDF. We know what the CDF of an exponential looks like, so we can directly use it over here as well, as the question hasn't asked us to derive it. In this case, PDF of this exponential random variable is of the form. So the CDF is of this form: fx of x is 1 minus e minus lambda x, which would just be 1 minus e minus 1 by 2x for x greater than equal to 0 and 0 otherwise. So probability x is greater than 2. First, this is not in the form of a CDF, right? CDF is in the form fx of x is probability x is less than equal to x. So we have to, this is essentially the probability x is less than equal to x. So we have to first rewrite it into the form of a CDF, right? We need to get it in the form of the CDF of x. So we'll use a complement rule for this. This is 1 minus probability x is less than equal to 2. So we're using a complement rule to get it in the form of the CDF. Complement rule, right, which says probability of A is 1 minus probability not A. Right, so here we have applied the complement rule. Once we apply the complement rule, now we can apply the definition of the CDF, right? So probability x is less than equal to 2 is just essentially F2, right? Definition of CDF, which is that fx of x is the probability x is, that was the whole point. That's why we use the complement rule so that we could get it in the form of CDF. So then after that, we can apply the definition of CDF. Now we want to find F2. Right, so we know for x greater than equal to 0 and 2 is greater than 0, we'll use this definition. Right? This is what the CDF is for any value of x greater than 0. So for x equal to 2, this would also apply because 2 is greater than 0. Right? So over here, now we'll just plug in instead of x2 over here. This will become 1 minus e minus 1 by 2. And then this would just again simplify to, and this would also give us the exact same answer that we got using a PDF. So we could either find this probability for this exponential random variable by using the PDF, because we know area under the PDF gives us probability, or because we know we know a closed form expression of the CDF like this, we could directly apply the CDF as well. The only thing is, whatever probability you have, you need to make sure you write it in terms of the PDF. Like over here, this was probability x is greater than 2. So we using the complement rule helped us write it in the form of CDF so that then we can use the CDF.